Microcontrollers. This is a basic choice for n number of applications, as all of we know. That is, many embedded systems are developed using microcontroller. Applications starting with home applications or office application, automation industry application. So variety of applications are there. As far as microcontroller and microprocessor is considered, there are some basic differences, as all of we know that. In general, microcontrollers are used to execute single tasks with an application, whereas microprocessors are used for bigger applications. Especially microprocessors are developed for computers, personal computers. In general, microcontrollers are used for the typical embedded systems. And microcontrollers designing and hardware is comparatively low cost, whereas processors are comparatively expensive. Microcontrollers are very easy to replace, but processors are not that much easy to replace. Microcontrollers, it is built with CMOS technology, which requires less power to operate. And here, as far as microprocessors are considered, its power consumption is high because n number of controls and the entire system it is supposed to control. Microcontroller, as far as concerned, consists of CPU, RAM, ROM, IO ports, and a number of other add-on registers. As far as microprocessor considered, it doesn't consist of RAM, ROM, and IO ports. It uses its pins to interface the various peripheral devices. Microcontroller is a small and low-cost kind of a microcomputer. General microcontroller, as far as considered. In general, microcontrollers are classified as 8-bit microcontrollers or 16-bit microcontrollers or 32-bit microcontrollers. As far as memory is considered, they are classified on the basis of external memory microcontroller, and second one is embedded memory microcontroller. And as far as instruction set is considered, then microcontrollers are further divided in two categories. One is CISC, that is CISC, and another one is RISC, that is RISC. So in general, as far as microcontrollers are considered, then they are the building blocks of embedded system. At 8051 microcontroller is one of the basic type of microcontroller designed by Intel in 1980s around, marketed in 1981. This microcontroller was based on Harvard architecture and developed primarily for use in embedded systems technology. Normally, this microcontroller was developed using NMOS technology, which requires more power to operate. Conventionally, before 8051, from n number of companies, it is made available in the market. There are mainly four popular companies like Freescales, then Intel's controllers, Zilog, and Peak. So all of them are from microchip technology. In Intel, redesigned microcontroller 8051 using CMOS technology, and their updated versions came with the letter C in their name. For instance, in 8051, it is an 8-bit microcontroller. These latest microcontrollers require less power to operate as compared to their previous versions. 8051 microcontroller has two buses and two memory spaces of 64K into 8 size of program and data units. It has 8-bit processing unit and 8-bit accumulator units. In general, as far as applications are considered, some of the applications in daily life or industrial applications, they are just listed here in general. So light sensing and controlling devices, temperature sensing and controlling devices, fire detection and safety devices, automobile applications, defense applications, and so on. Some industrial applications include industrial instrumentation devices, process control devices. As far as 8051 is considered, there are measurement related applications also, like voltmeter measurement, then measuring and revolving objects, and current meter objects, handheld metering systems, and many other. So these are some of the main application areas. Just as an introductory part, I have listed out here. Now mainly, as I mentioned, controllers are divided based on instruction set in two categories. It is instruction set, as we know that it is a kind of a group, and based on the addressing modes we are classifying them. Instructions based on instruction set, the architecture called CISC is nothing but the architecture where it attempts to minimize number of instructions per program, and it sacrifices to certain extent in terms of number of cycles. And as far as reduced instruction set architecture is considered, it exactly is doing opposite, reducing the cycles per instruction at the cost of the number of instructions per program. Now, in general, if we talk about CISC architecture, then it is just the earlier machines, they were programmed in assembly language and memory was slow and expensive. The CISC philosophy made sense and was commonly implemented in large computers, then DEC systems. Then slowness of memory access prompted designers to create instructions which reduce the frequency of memory access and also the memory size. That was the main thing. The RISC philosophy, whereas in early days that was used by the computers primarily in assembly language or machine language, and this promoted powerful and easy, no doubt, tried to make instructions to do as much as work as possible. With the arrival of higher level languages, computer architects also started to create dedicated instructions to directly implement various mechanisms similar to higher level language programming. Another goal, it was provide every possible addressing mode for every instruction, since hardware design was more mature than compiler design, and designers tend to implement parts of functionality in hardware rather than in memory constrained compilers. In case of CISC architecture, typically complex instruction set decoding logic is used. It is driven by need for a single instruction to support multiple addressing modes, small number of general purpose registers, several special purpose registers. Then many CISC designs set aside special registers for the stack pointer, interrupt handling, and so on. So this can simplify hardware design somewhat at the expense of making the instruction set more and more complicated. As far as RISC is considered, then it is a reduced instruction set. So definitely architecture that utilizes small, highly optimized set of instructions rather than more specialized set of instructions. Prime difference between RISC and CISC is the number of and complexity of instructions. In 70s, early 80s, designers started looking at simpler instruction set architectures. So very few set of instructions, and then certain designs, that is one cycle execution time and pipelining, and considering the number of registers, so the instructions were defined. Few data types, then very simple addressing modes, and as far as the architecture is considered, the Harvard architecture, the RISC designs often use a Harvard memory model where the instruction stream and the data stream are conceptually separated. So pipelining, unique feature of RISC, is also one of the biggest advantage. In case of CISC in general, there is emphasis on hardware. In case of RISC, emphasis on software. In case of CISC, it includes multi-clock. In case of RISC, it generally uses single clock. In case of CISC, it is complex. Here it is reduced. Here memory to memory, load and store incorporate in instructions as far as CISC is considered. Here RISC, register to register, load and store are independent instructions. And in case of CISC, high cycles per second, small code sizes. In case of RISC, row cycles per second, large code sizes. In case of CISC, transistors used for storing complex instructions. And in case of RISC, it spends more transistors on memory registers. So to summarize, just I have listed here. In general, in CISC, largest set of instructions, easy to program. In case of RISC, smaller set of instructions, difficult to program. In case of CISC, simple design of compiler considering larger set of instructions. In case of RISC, complex design of compiler. In case of CISC, many addressing modes causing complex instruction format. In case of RISC, few addressing modes, fixed instruction format. In case of CISC, instruction length is variable. In case of RISC, instruction length varies. In case of CISC, higher clock cycles per second. In case of RISC, lower clock cycles per second, single clock most of the times. In case of CISC, emphasis on hardware, here it is in software. And in case of CISC, control unit implements large instruction set using microprogram unit. In case of RISC, each instruction is to be executed by the hardware. So these are some of the facts as far as architecture is considered. CISC and RISC architecture, from microcontroller point of view, it plays very important role. Now we will move the basic architectural say approach. There are two main approaches. First one is called as von Neumann architecture, and the second one is called as Harvard architecture. Now as far as von Neumann architecture is considered, its theoretical design is based on concept of stored program computers where program data and instruction data are stored in the same memory. You can see in the picture. Then the architecture was designed by a renowned mathematician and named John von Neumann. He was also belonging to physics department. Until the von Neumann concept of computer design, computing machines were designed for a single predefined purpose that would lack sophistication because of manual rewriting of circuitry. The idea behind von Neumann is ability to store instructions in memory along with data on which the instructions operate. Von Neumann architecture refers to general framework, that is the computer's hardware, programming and data should follow. The architecture consists of in general the components like there is a memory space, instruction decode and process and built-in registers. In general we can have a ALU, CPU and control unit with registers. ALU is responsible for carrying out all arithmetic logic operations, whereas the control unit determines the order of flow of instruction that need to be executed programs by issuing control signals to the hardware. The registers are basically temporary storage locations that store addresses of the instructions that need to be executed. The memory unit consists of RAM, which is in the main memory used to store program, data and instructions. The I/O interfaces allows the user to communicate with the outside world, that is nothing but mainly the storage devices. Now as far as Harvard architecture is considered, so here you can see it is a simple again computer architecture, separate storage and single pathway for program data and instructions. Unlike von Neumann architecture, which employs a single bus to both fetch instructions from memory and transfer data from one part of the computer to another, Harvard architecture has a separate memory space for data and instruction. So here you can see the two spaces, separate spaces. Both concepts are similar except that the way they access memories. The idea behind the Harvard architecture is to split the memory into parts, one for data and another part for the memory, so a part of the memory for programs. The term was based on the original Harvard Mark I relay based computer, which employed a system that would allow both data and transfers instruction fetches to be performed at the same time. Here you can see the register space, data bus and address bus separately connected. In case of von Neumann, it is a single bus, bidirectional single bus. Real world computer designs are actually based on modified hardware architecture and commonly used in microcontrollers and DSP processors. As far as basic difference we can state here, that is in von Neumann architecture, single memory to be shared by both code and data. Harvard architecture, separate memories for code and data. Von Neumann architecture, processor needs to fetch code in separate clock cycle and data in another clock cycle, so it requires two clock cycles. In Harvard architecture, single clock cycle is sufficient as separate buses are used to access code and data. In case of von Neumann, higher speed, thus less time consumption. Then in case of Harvard architecture, slower in speed, more time consuming. And in case of von Neumann, it is simple in design. Comparatively, Harvard architecture is little bit complicated. Addition to this, we can comment that simple control unit design and development of one is cheaper and faster as far as von Neumann is concerned. And in case of Harvard, control unit for two buses is more complicated. So definitely it is expensive one. In case of von Neumann, it uses same physical memory address for instruction and data. and in hardware it uses separate memory addresses for instruction and data. Von Neumann architecture used in personal computers, laptops and workstations especially. As far as hardware architecture is concerned, it is used in microcontrollers and signal processing mainly. Now as far as features of 8051 is considered, before going for that, we will little bit have a comment on role of microcontroller and what exactly is the criteria while choosing the microcontroller. Basically, speed is the primemost criteria. The highest speed that microcontroller supports, the question is raised, and based on that, controller is selected. Secondly, packaging. Then the question is, does it come in 40 pin DIP or dual inline package or quad flat package or some other packaging format? This is important in terms of space, assembling and prototyping the end product. Then power consumption, that is also a big issue. So this is especially the criteria and it is very critical where battery powered products are to be developed. Then amount of ROM and RAM, that is a memory, the number of IO pins and the timer on the chip, how easy it is to upgrade to higher performance or lower power consumption versions, and the cost per unit. This is also very important fact while choosing the particular microcontroller for the particular application. This is general criteria like speed, packaging, power consumption, amount of ROM RAM, number of IOs, then cost per unit. Secondly, there may be consideration is availability of assembler, debugger, and whether it is a cross compiler, kind of a C language compiler, emulator, technical support, in-house and outside wherever it is needed. So third party vendor may be involved. So that is also one question. And again, one more is also prominent. That is whether it is a 8-bit controller, that is available in diversified modes like from multiple sources. So which supplier and which kind of package and which is best suitable, like we get it from Prescale, Zlog and Microchip Technology, all dedicated massive resources to ensure wide and timely availability of the third product, their products. So it is a stable one as far as product is considered, and you have to opt which one is best suitable for you. Now based on all this discussion, now we will move to the actual controller which is part of our curriculum. So that is 8051. So first of all, let us go through the main features. So it is a 4 KB bytes on chip program memory, that is ROM, 128 bytes on chip data memory, that is RAM, 4 register banks, 128 user defined software flags, 8-bit bidirectional data bus, 16-bit unidirectional address bus, 32-bit general purpose registers, each one 32 general purpose registers, each one is of size 8-bit. Then there are 16-bit timers. There are mainly two timers, so timer 0 and timer 1. Then there are 3 internal and 2 external interrupts. We will talk in detail on each one of them, that is interrupts and timers and everything. Then there are 4 8-bit ports. Short mode have 2 8-bit ports. Then 16-bit program counter and data pointer. And moreover, 8051 may also have number of special features such as UARTs, ADC and some operational amplifiers, etc. Now in general, if we go through the block diagram of 8051, here you can see there is interrupt control section, CPU, oscillator, bus control, 128 byte RAM, 4 kilobyte ROM, timer 0 and timer 1, timer counter, both way it is useful, serial port, IO ports P0, P1, P2 and P3, address and data ports, and there are like bus control. So these are this is the general structure. So here is a kind of architecture. So there we get interrupt control, CPU, oscillator, 4K flash, 128 RAM, counter timer, bus control, IO ports, and general bus control. So this is the figure taken from the actual uh, say the data sheet. Like if we brief about what are the major units as far as consider in short, then ALU is the primemost component. So this is the arithmetic logic unit which is going to carry out all the operations, uh, logical and arithmetic, addition, subtraction, your AND, OR, XOR, and so on. Program counter is a PC and that is 16-bit register and has no internal address. The basic function of program counter is to fetch the address of the next instruction to be executed from the memory. Then the PC that holds the actual next instruction residing in the memory, and when command is encountered it produces that instruction. The PC increments automatically holding the address of the next instruction. Then registers, there are a number of registers like mainly A and B. These are conventional traditional registers. Then there are serial port data buffers, SBUF, timer counter mode control register, that is TMOD. There is a power control, PCON, interrupt enable control, IE, timer counter control, TCON, serial port control, SCON, then interrupt priority register, data pointer, DPTR, and many more. Then internal RAM and ROM as far as consider, ROM is 4K incorporated on chip. It is non-volatile memory. Its contents cannot be altered and hence has a similar range of data and program memory. That is, it can address program memory as well as 64K separate block of data memory. Then RAM as far as considered, 8051 is composed of 128 bytes of internal RAM. This is volatile memory since contents can be erased and they are lost rather once power is switched off. Then 128 bytes of internal RAM divided into 32 working registers. So in turn there are 4 register banks. For memory organization we will talk in detail. As far as ports are considered, P0, there is no external memory present. This port acts as general purpose input output port. Port 1, this is used for various interfacing activities. A normal IO port. Port 2, that is P2, similar to port 0. This port can be used as a general purpose port when there is no external memory. But when external memory is present, it works in conjunction with port P0 as an address bus. This is 8-bit port and performs dual functions. Port P3, this behaves as a dedicated IO port. Interrupt control as far as considered, then this is used to suspend or halt the normal program execution for a temporary period of time in order to serve the request of another program or hardware device. Any interrupt can either be an internal or external. So this is going to suspend. As far as there are two ways microcontroller is considered. One is by sending software instruction from the program, and the another one is sending hardware signal. The interrupt mechanism keeps the normal program execution in put on hold mode and executes subroutine program. After the subroutine is executed, it gets back to its normal program execution. This subroutine program is also called as interrupt handler. The subroutine is executed when a certain event occurs. So there are 5 main interrupts, 2 external interrupts, that is INT0 and INT1, and 3 external interrupt sources, that is serial port interrupt, timer 0 and timer 1. So mainly this is about interrupts. In case there is a ALE, address latch enable, external address, that is EA pin, PACN, program store enable, and RST, that is reset. So these are also very important pins. Data pointer, that is DTPR, is DPTR is 16-bit register, DPH and DPL divided in 2 parts. Stack pointer, it is 8-bit register. Purpose is to access the stack. It is 8-bit, so it can take values from 00 to FF. It acts as a pointer for an address that points to the top of the stack. Data bus and address bus. Data bus is to transfer data, and electronic channel using which data is going to travel. And address bus, purpose of address bus is to transfer information but not the data. The information tells from where the data should be sent or to receive from. The capacity of memory of the address bus depends on the number of wires that transmit the signal address bits. Program status word is Generally, there are 4 math flags: carry, overflow, auxiliary carry, and parity, and 3 general purpose flags, that is F0, GF0, and GF1. We will go into detail afterwards. Serial data communication, there is serial data mode 0 and serial data mode 1, serial mode data mode 2, and serial data mode 3. RxD and TxD, these are the 2 pins. SBUF is a register, and with the help of SCON register, that is a serial control register, it is going to, and power control register, that is SCON and PCON. These 2 registers, it is going to manage the data transfer with the 2 pins RxD and TxD. So all together, this is about the general block diagram architecture of 8051. 8051 family members as far as consider 8051, 8051-2 and 8031. So feature wise, ROM in 8051 4K, 8052 8K, 8031 0K. RAM it is 128, 256 and 128. So timers in 8051 2, in 8052 3 and 8031 2. IO pins in 8051 32, 8052 32, 8031 also 32. Serial port in all of them 1. And interrupt sources in case of 8051, actually there are 6 sources, but conventionally only 5 are used. And 8052 8 and 8031, there are again 6 sources. So this is all about some basic part related to 8051 microcontroller. In coming sessions, we will go into details about the architecture, about the pinout, about the addressing modes, about memory organization and instruction set before going for the program. Thank you.